All right, question 1, mock final from 2018. We're going to dig right in here and start right away. First question says, magnesium burns in air with a dazzling brilliance to produce magnesium oxide and gives the balanced chemical equation here. How many grams of O2 are consumed when 18.7 grams of magnesium burns? So this is a stoichiometry question. First thing we need to do is convert our grams of magnesium into moles, because for stoichiometry we always deal in moles. So our moles of magnesium will be equal to the mass of magnesium over the molar mass, which is 18.7 grams, divided by the mass from the periodic table, which is 24.305 grams per mole, 0.769 moles. Now we have to figure out how many moles of oxygen need to go with this many moles of magnesium. We know from the balanced equation that we need 1 mole of oxygen for every 2 moles of magnesium. So to find moles of O2 needed, that's going to be equal to the moles of magnesium multiplied by the ratio of the two coefficients, which is going to be 1/2. Times 1/2 is 0.385 mole. Question wants the number of grams of oxygen, so we need to convert that moles into mass. So the mass of O2 is the moles of O2 multiplied by molar mass of O2, 0.385 mole, multiplied by the molar mass, which is 31.998 grams per mole, 12.3 grams. That's good. We're going to go to the next question, which is question 2. So question 2 is a sigfig calculation question. We're going to do this according to order of operations, and we're going to calculate the correct number of sigfigs at every step. So the first calculation is the multiplication, and our answer should have the same number of sigfigs as whichever number we're multiplying that has the fewest number of sigfigs, which should be the 3.862. So our answer should have 4 sigfigs. So we get 6.036 minus 5.98. For subtraction, our answer should have the same number of sigfigs, same number of digits after the decimal as the number with the fewest that we started with. So that is equal to 0.056, but we can only have 2 digits after the decimal, so the correct number is 0.06 to the right number of significant digits. All right, next question is number 3. Potassium dichromate is used in tanning leather, decorating porcelain, and waterproofing fabrics. Calculate the number of chromium atoms in 78.82 grams of K2Cr2O7. So this question gives us the number of grams, so it gives us mass. We're going to convert that mass into moles, and then from moles, we can convert that into the number of atoms. It's kind of the logic we're going to follow here. First step is to get the moles of K2Cr2O7. That will be equal to the mass over the molar mass, 78.82 grams, divided by 294.185 grams per mole. That equals 0.2679 mole. For the moles of chromium, that actually equals 2 times the moles of Kr2O7 because we have 2 chromium atoms in every mole of, or in every formula unit of K2Cr2O7. That's 2 multiplied by 0.2679 mole. Equals 0.5358. The number of atoms of chromium is going to be equal to the moles of chromium multiplied by Avogadro's number, 0.5358 mole, 6.022 times 10 to the 23rd atoms per mole, 3.227 times 10 to the 23rd atoms. All right, we are on question number 4. How many kiloliters does 8.55 times 10 to the 8 centiliters sample contain? So this is just a unit conversion. We have 8.55 times 10 to the 8 centiliters. And the unit factor is that there's 10 to the power of 5 centiliters in a kiloliter. So we can do that like so. And that equals 8.55 times 10 to the 3 kiloliters. Question 5. Household sugar, sucrose, has the formula C12H22O11. What is the percentage of oxygen in the sucrose by mass? All right, so what we're going to do here is figure out for the formula unit what the mass of carbon, the mass of hydrogen, and the mass of oxygen are. And then the percentage of oxygen will be the mass of oxygen over the total mass. So to begin with, the mass of carbon is 12 times the molar mass of carbon, which is 12.011 grams per mole. That's 144.132 grams per mole. Hydrogen next. Mass hydrogen is, we have 22 of these, 1.008. These numbers come right off the periodic table, 22.176. Finally, we have mass oxygen is 11 times 15.999 grams per mole. 175.989 grams per mole. Our mass total is the sum of these three masses, which is 342.297. The percentage oxygen then is the mass of oxygen over the mass total times 100%, which is 175.989 grams per mole. 342.297 grams per mole times 100%, 51.4%. And that is that question. Question 6. Balance the following equation for the combustion of benzene. C6H6 plus O2 goes to water and CO2. So we usually start by balancing atoms that only appear once. So carbon appears once on the left and once on the right. So to balance carbon, we need 6 on the right. So we can put a 6 in front of the CO2. Next, we're going to balance hydrogen, which appears only once on each side. We have 6 hydrogens on the left, 2 on the right, so we can have 6 on the right if we put a 3, and it's not a 3 in front of the water. Then what we need to do is balance the oxygen last. And the oxygen is last because it appears twice on the right side. If you add up the oxygens on the right, you get 3 plus 6 times 2 is 12 is 15. So we need 15 oxygens on the left as well to balance this. To do that, we could put a 7.5 in front of the O2. Now, generally speaking, we don't like having decimals in our coefficients, so we can get rid of that decimal by multiplying everything through by 2, which would give us 2 C6H6 plus 15 O2 goes to 6 water plus 12 CO2. I have 3 here. These are quick. Question 7, a red glaze on porcelain can be produced by using MnSO4, which is manganese sulfate. So Mn is manganese. Now, manganese is one of those elements that can actually take more than one possible charge. So in this example, we have sulfate, which is SO4 2-. That means the manganese must have a charge of 2+, which means this is manganese 2. And sulfate is the anion there. Next one is name the compound. These are all nonmetals. So this is not an ionic compound. Therefore, our name for this should be dichlorine for the 2 Cl's, pentoxide. This is a weird example too, where usually it's penta, but if there's an O that's right after penta, we drop the A, so it's pentoxide. What's the formula for ammonium phosphate? Ammonium is NH4+, phosphate is PO4 3-. So in order to balance the charge, we need 3 ammoniums. So our balanced equation will look like NH4 3 PO4. Now on to question 10. The percent composition by mass of a compound is 76% C, 12.8% H, and 11.2% O. The molar mass of this compound is 284.5. What is the molecular formula of the compound? This one's a bit longer. When you get a question like this where it gives you the initial percentages of these compounds, I usually find it easiest to begin by assuming we have 100 grams of the compound. That means then that our mass of carbon we can get directly from the percentage is going to be 76.0 grams. Mass of hydrogen, 12.8 grams. Mass of oxygen, 11.2 grams. So we have the mass ratio. We know what the ratio of these 3 masses are to each other. What we really want, though, is the mole ratio, because the molecular formula is really just the mole ratio of the different elements that are in there. So we're going to convert each of these 3 masses into moles. So moles of carbon is mass over molar mass is 76.0 grams over 12.011 grams per mole. That equals 6.33 moles. For hydrogen, moles of hydrogen is mass, 12.8 grams divided by 1.008 grams per mole, 12.7 mole. Didn't leave myself a ton of space here. But our moles of oxygen is mass over molar mass again. 11.2 grams over 15.999 grams per mole. 0.700 moles. So now we know the ratio of the 3 moles, and we want a whole number ratio ideally. So what we're going to do here is divide each one of these by the smallest, which is 0.7. Which gives us a ratio of 9 to 18 to 1. So we know that our compound must have an empirical formula, C9H18O. Now we don't really know at this point if that's the molecular formula or not. We know this is the empirical formula. But from the empirical formula, we can tell what the molecular formula will be using the molar mass that's stated in the compound. So to do this, what we do is we calculate the molar mass of the empirical formula by adding up 9 carbons, 18 hydrogens, and 1 oxygen, and that gives a molar mass of the empirical formula of 142.242 grams per mole. We know our actual molecular formula, molecular weight, is 284.5 grams per mole. So we divide that by the empirical formula weight, which is 142.242, equals 2. So that means the molecular formula has 2 times as many atoms as the empirical formula, so that our molecular formula will be C18H36O2.